I am impressed at how many people are here to actually learn to count to 1 today. I mean, for this late in the afternoon is really impressive. So, you got both hands, right? We can do this. See, 0 and 1. We're good. All done. No. So a little bit more than that. You know, from a routing, switching, everything that we do point of view, binary is what everything is going to boil down to. And there's lots and lots of different applications that we can get to for how we're going to use it. My concern in here is to get us comfortable with things, to make binary come to us easier, to make other things easier, such as dealing with access lists or route summarization or things along those lines, particularly with regards to certification exams. Now, subnetting, that stuff will cover all the tracks, all levels of every track, so you're going to have to do it at some point in time. We're also going to have to do more of it with IPv6, because that's kind of coming. Oh, speaking of, I've got a great IPv4 joke. Okay? Did you hear about IPv4 went into a bar and said, I'm exhausted? So anyway, that's the extent of that. I'm here all week. But beyond that part, things like that from a subnetting and summarization standpoint, binary will make our life a lot simpler, even in the IPv4 space. Okay? So dotted decimal stuff, as well as when we get into the hexadecimal for IPv6. In addition, when we start thinking about access lists, and that focus from a certification standpoint is more on the CCIE level, okay, because we get into what we call strange access lists, or things that no sane person would ever want to do. But we'll get there. So 1 step at a time, or 0, then 1 step at a time. So anyway, Zen in the Art of Binary Math is where we're here. I am Scott Morris, your tour guide for this evening. Don't worry about the agenda stuff. We'll get to the things as we get to it. We are going to learn to count, hopefully without your fingers. Because again, it's just 0 and 1. Should be okay. A little bit about me, just in case you don't know who I am. I get around. That's probably the easiest way to describe it. So I've been through the certification tracks, many of them along the way. I have trained all sorts of people from CCNA on up over the years. Lots and lots of CCIE training and a myriad of other stuff along the way. As you can tell by all the little things on the bottom, I like pretty logos, and I also get bored very easily. So kind of a good ADD engineer. I like to hop between things. But enough about that. Do what? What's Juniper? Some awesome stuff. No, can't talk about that. I think you're going to have, when we go back to the recording, you're going to hear a beep. Okay. So all the good stuff. Anyway, session goals in here. Like I said, I want to make sure you guys can count to 1. That is a very important thing in here. We're going to start with stuff that you know, which honestly, I think you've already demonstrated you can count to 1. So this is a good start. We are rocking and rolling so far. And then we're going to move beyond your comfort zone. So we're going to take things beyond where we typically would, or where normal people typically would anyway. Bottom line, some things are going to seem foreign. Not a problem. Okay? We'll experience them. We'll go through them. We're going to find all sorts of new and exciting ways for things to work. If you are sitting in the CCIE lab, there is nothing that is considered abnormal. Or the flip side is that everything is considered abnormal. Either way you go. Okay? How many of you are working on your CCIE lab right now? Wow, a couple of you. All right. So let's see. CCNA level. Cool. Good. NP? All right. Excellent. So wide variety. Anybody hate certifications? Excellent. I saw some of the same hands, but we're not going to go there. All right. So the art of binary itself. Okay. Now this is a thought process game. I have 2 coins in my pocket that add up to 15 cents. One of them is not a dime. So what do I have? And no, there's no foreign currency involved. Absolutely. I said one of them was not a dime. It has nothing to do with the other one. This gives you an idea of how to think based on the way that Cisco writes exams. Right? They will tell you something. You may have an assumption of what it is and limit your thought process based on that, but follow things explicitly. That will help you out a whole lot, specifically, or I guess explicitly, on the CCIE level exams. Right? So very important things to it. But in our case, there's only going to be 2 options for a bit to be here. So whether it's a 1 or a 0 should not be a difficult choice. At least I hope not. On the other hand, if you're male, you have a 90% chance of getting a 50-50 question wrong. Ask any of the girls around here. So key, though, is knowing what the bits are actually there to represent. Why are the bits there? The router thinks in binary. So if we can do the same thing, or at least understand that level of thinking, we're that much closer to knowing what's going on with the router at any point in time, or switch. All right, so that'll make our life a whole lot easier in there. Subnetting, as we get into, we talked about this before from our drawing standpoint, you draw lines. Everything over here is a network or a subnet. Everything over here is a host value. We can move that line wherever we want to, but it's all about the lines. Access lists, on the other hand, are each bit itself in an on or off position. I would say it's kind of like Christmas lights, but that's only like the newer Christmas lights. Old Christmas lights used to be like subnetting. When one went out, everything further down went out. All right, so that was our line. Nowadays, though, all the cool LED ones, we can have one out, and all the rest of them are still working perfectly fine. Okay, much easier to spot the problem with it. But knowing what your bit, whatever bit we're talking about is, what it's doing, will help define what you can or can't do with it. So let's start out with the wonderful world of IPv4. You guys know what that is, so it's all good. 32 bits of addressing, right? We have, well, different bits in here. I like to think, and I don't know why I made them X's and not H's, but I like to think in terms of the job of the bits that we're talking about. So my network bits are N's, my subnet bits are S's, and usually, apparently when I'm awake, I'll make the host bits into an H because that would make much more sense. So as we get in here, we have all these bits to play with. Now, they're represented in a dotted decimal format, right? Does the router care? No. Router doesn't think that way. That's for us. Because if we spit it out all in ones and zeros, that would just confuse the crap out of everybody. So not going to do that stuff. So we go through here and define what our network side is or our host side is based on, what's the most important thing in a network address? My subnet mask or my net mask. Okay, because that's going to tell me where that line is in terms of how I define this. So when we get into binary, especially from the summarization standpoint, we got to figure out that line and then determine where I'm going to move it to. We get all those questions about, how many different subnets can this have or whatever it's going to go with. But let's kind of start with some obvious things, or some simpler things anyway. Off the top of your head, if I was going to build an access list to summarize something or to deny certain things, how efficiently can I do this? Do you notice anything obvious about the numbers when they're up there? Okay, they're what? They're in order. Well, okay, that's true. Okay, so from a counting standpoint, that makes my life easier. What about binary, though? Okay, you said they were discontiguous? Oh, contiguous. Okay, so they're in order. That's right. But from a binary standpoint, is there anything that jumps out? Now, if the answer is no, that means that you have to start thinking about converting this into binary and kind of have that as your first place to go. Okay? Okay, well, that's true. So my first two octets are identical, so that will make it a whole lot easier. Everything will be in the 172.16 range. But if I'm going to come up with an access list or I'm going to come up with a summary address, either way we want to think about it, what is special particularly about 31 and 32? Okay, they cross what they call a bit boundary. Okay, something changes in there where they're no longer grouped together. There's a lot of difference in between it. All right? So when we start looking at the details in the binary, once we break it out, it's a lot easier to see that this one is significantly different than this. 32 and 33, there's one bit of difference. There's a different bit of difference right here when I get to 34. But now is the idea that I see it in binary, and I can start grouping or not grouping things together. And again, whether I'm doing it into a route or into an access list, this thought process becomes very important for putting down what I'm going to do and not getting this huge, overlapping set of addresses in here. If I'm doing access lists, I guess it's more important. You don't want to permit or deny too much. But even in route summarization, I wouldn't want to accidentally stick in a route for the whole 172 network when really all I wanted was those 4 or something as close to it as I could. Be specific, and the binary will help you see that part. So when we get down here, okay, I can summarize as what we call a /18. Now, drawing my line. If we notice, as far as each of the binary bits goes, this line right here is where things start to get different. So if I'm told that I have to do a route summary, I want one network in order to advertise all of those. That's where I need to draw the line. The concept that I get into, and this is access list or route summary, is same or different. Okay? And that's exactly where we have to be. So right up to this point right here, I'm the same on all 4 of the things that I have. So if that's where I draw my line, 172.16, okay, so there's 8 bits, there's 8 bits, and there's 2 more, that's how I got the /18 as far as a mask goes. Right? So it's all in the number of bits. I mean, I could have written the whole line out in binary, but that would bore you guys, and me too. So, okay so far? All right. Now, when we get into things like access lists and our concept becomes, am I just filtering those and nothing more? Or am I just doing it for a whole route and I don't care about the extras? Security-wise, I want to think of it as no more, no less. And again, my thought process is being on the CCIE lab as far as access lists. So no more, no less. And that probably should be real life too. Because these are all so different, I can't do it in one single line. Or I will permit way too much or deny way too much, whichever way that I'm going in there. So we need to find ways to break it down further as to where my differences are or aren't. Now obviously I can do it in 4 lines. Okay, that'd be kind of the easy way to do it. Just write an access list, permit each one by itself, we're good to go. Yeah, except the lab will tell you to do it in as few lines as possible. Whenever you see those words, be afraid. Okay? So that means that I've got to find something where I can group them together on a binary level. Now, I certainly can't do it with 31. Okay? Way too many bits that are different. So that one has to be by itself. We're good to go there. If I get down to the next 3, okay, now I have 2 bits that are different there. When I write something out in binary, when I'm looking to permit all values, I'm going to kill myself here. When I'm looking to permit all values in binary, dry erase, okay. I have to account for everything. And that means that with 2 bits, I have 4 possible values, or 2 to the 2nd power if you want a quick check. I have to account for all 4 of those values. Not counting the first line, do I account for all 4 of them right here? I'll give you a hint. The answer is no. Okay? No, because there's only 3 of them. So I'm missing something else in there. Okay? Now, here's another interesting thought process, just to kind of make your mind explode a little bit more. There's 2 ways to accomplish this with exactly the same number of lines. Okay? So notice I'm doing a permission for my access list. I got the 31 line. Again, that's by itself. We're good to go. Now, what I did is I went ahead and grouped 2 things together that I could get into one line, which was 32 and 33. Only 1 bit of difference between them. So that made it a /23. Kind of a simple way of putting that in there, but only that 1 bit being difference, drew my line, good to go. And then treat 34 all by itself. The other way that I could do that, okay, is to deny one. Now, if an access list, I have to deny first. Okay? So I would deny 35, which is my missing entry, as a /24, and then I would permit 32 as a /22, so giving the 2 bits in there as being different. Still results in 3 lines either way I go. But that, from a binary perspective, is making things as tight as possible without giving the router extra stuff to think about, without giving you extra stuff to think about, or more importantly, getting the points on the exam. And that's what it all boils down to. You're scowling. Well, so the good news is on the CCNA exam, there is nothing going to be like that where you've got to do least number of lines possible. So you're good. Okay. Yeah. For summarization, right. If I was told to summarize all of these, that's only about drawing the line. And yes, it would cover other things, but yeah, that's just the way that it's going to go. All right, so kind of keep it simple first, then we make it more complicated as we grow up in the certifications. All right. Cool so far. Questions, thoughts, comments, rude remarks? If you want them on tape, you got to talk to the microphone. All right. So 1 step at a time. So what if we add a little gas to this? All right, so I'm adding a few more networks in here. Good news is, same thought process. And that part hasn't changed. We just got more stuff to deal with. All right? All right. All right, so that was an animation failure. Anyhow, so what's supposed to happen is, again, breaking these out into binary and noticing the differences. 31, still completely by itself. Now, I do have 32, so let's go back over to here. If I had 3 bits which are different, how many values do I have to have? Right, 2 to the 3rd power. I have to have 8 values. Not counting the first line, how many things do I have there? Okay, got 6 of them. So 6 does not equal 8. So again, I'm going to be stuck in that same position right there of how best to write the access list to do it. And again, 2 ways to think about that. So I can either do the permit of 31 all by itself, which I got to do in either one of them. I can deny what the extra stuff would be. Actually, that's a typo. That should be a 1 right there. My bad. All right. So deny 38 and 39. This will permit from 32 all the way to 39. Or I can do it with the 31. This will do 32 through 35. This will do 36 and 37. I got different methods of thinking about for it. Now let's step back to looking at it as a summary. And I don't have this on the slides, so you guys have to think a little bit. If I told you that I wanted to make a summary address, so whether, pick OSPF or FBI, GRP, I don't care. If I needed to make a summary route to cover all of those networks, what would it be? Okay. Between 2? Well, so 16, 17, 18, 19, 20. So you're saying I can draw the line right there in the middle of those 4 bits? Okay? Yeah. So remember, I have to go to where the first difference is if I'm drawing my line, which is still, just like we looked at last time, going to be my /18. Now, interesting way to check with that. When I go to a /18, so this bit right here, you guys have all written out binary tables, right? So the 2, the 4, or I guess 1, 2, 4, 8, 16, 32, all that jazz. Okay? What position is this bit right here? 64. There you go. So you can do an automatic check in your head of exactly how many networks I'm going to get. And with the /18, anything less than 64 is going to match in there. So my 31, that side of it, and the 32 and up, all the way to 63. Whatever the last bit, so if I draw my line right here, so whatever my least significant bit is, the position that it happens to be in will tell me how many further matches there are. So the numbers that will match it will be 64 of them. If my starting point is 0, then it's between 0 and 63. If my starting point is 128, it's between 128 and 191. 64 things that would match a /18. So /18 says that I draw my line here, and the rest of the bits you can do whatever you want with, but like if I was subnetting out of this, then that would tell me how many different possible subnets that covered. Yeah, so possible values in there. Say that again? That would be your increments, yes, absolutely, or block size. Yes. Now, stepping away from routing side, okay, we're going to think only access list for a minute. And this is where life is going to get a little bit interesting. So first, from a conceptual standpoint, I want to think about making an access list to only get even /24s. Only even numbers is what I want to match. Huh? Get rid of the 1? Well, then it'd just say 92.68. Oh, okay, you mean the 1 bit, okay. Yeah, so, and that's where we're going to think about things. So whenever you get a thing like that, pick some samples. If I know I'm getting even numbers, again, going back to binary, go take a look at this right here. Okay? Out of any of the values, and we could pick anything, I probably should have put 254 on there just for fun, But the idea is, what is in common? What is the same on all of them? Okay? The value in this 1-bit position right here is always going to be a 0. Now, here's kind of an interesting thought, and I have no eraser. Cool. It's over there? Oh, there you go. Thank you. So whenever you look at access lists in documentation, they'll tell you that you've got a, permit a network, permit a mask. Eraser probably sucks. Permit a network and the net mask that goes along with it. And it's always described in the same fashion as when you're typing an IP address. Address and mask, okay, which is sort of accurate, but it's not the same. Okay, masking bits are going to be treated a little bit differently from an access list perspective because of the fact that I don't have to draw a line. I'm giving you a mask that simply says where a 0 value means my starting point must stay the same. So whatever number I'm starting with, if the mask is 0 for that bit, it must stay the same. A 1 means don't care. Okay, so if you think about a basic access list. I want to permit everything in 192.168.100.0, that whole network, that whole /24. Okay, your mask is 000.255. Okay, what that means is the first 3 octets must stay the same because they're all 0 bits, and in that last octet, I don't care. Now, those examples are great because they're what we're used to, but again, we're drawing that line. What I'm telling you, though, is the router on access lists doesn't care about that line. Each bit is done individually. So when we start looking at requirements like this, as far as permitting all of the even subnets in here, what do I know? What's my starting point? If I were going to write the access list to do this, how would I write it out? Okay, so 192.168.0.0, that's my starting point. It just happened on there, but okay. So this sets my bits to begin with. This says where am I going to start? And then what I have to do is I have to create my net mask, which tells me which bits do I care about, which bits do I not care about. All right? And in doing that, these will all stay the same, those will all stay the same. When I get down in here, when I get down to my 3rd octet, is where life is going to be interesting. A binary perspective, I would have 7 1-bits. The only one I care about is that bit in the 1 position that must remain a 0. And then if it's, I guess, security, we can say 255 right here, whatever we're going to do. All right, there's my net mask to permit all of the even subnets. Now here's a tricky question. How would I get all the odd subnets? Nope. That's a good thought because that's where most people go with it. The point is, I'm not changing my mask because the concept will all be the same. I'm changing my starting point. So once I set this to a 1, remember, odd numbers will all end in a 1 from a binary standpoint. The same mask will work with that to get all odd numbers. From a mathematical perspective, the network portion of the access list is my binary starting point. And then the mask gives me my permissions to go along with that as far as what's going to be same or what's going to be different. Completely a different way of thinking about stuff, but this is the way that the router sees the world. So when we get down to that, that's the way to start thinking about what we call the bizarre or the funky access lists. So all the cool things that you get to look forward to as you move through your certification progression. But at the same time, getting used to this thinking, though, will help out a whole lot, even on IPv4 subnetting, but certainly when we get into the IPv6 portion of the world. All right, so good places to be at. Yes, sir. Yes, it will. Okay, so if I keyed it in as 192.168.2.0, given this mask, where it says in that bit position I don't care, I will always reset it to the lowest possible value. Okay, so the router will take care of that for you. Nothing you need to worry about. And that's also an interesting way to check my access list to make sure that I didn't mess something up completely. But otherwise, it will give you your binary starting point at the lowest possible value. Good so far? It's only going to get more fun, so that's why I want to be sure. All right, so our shifting gears, let's see. Put those, what's in common? Yep, there we go. So there's my mask. All right, now it's even more fun. Think about the access list about how do I come up with something like this and do it in as few lines as possible. All right. And this is the part where most people look kind of like, the dog when you go home. It's like, okay. That dotted decimal thing, that's not the way the router thinks. Router doesn't care. Very much like a honey badger. Okay, it is. It's all about grouping. Okay, so when we start to look at it, I'm going to kick this ass in here. So, what things are different? Okay, first octet for it happens to all be the same. So 168, we're cool. Second octet, I got a couple different variables in there. Break them into binary. I can see that the one bit of difference is right here. Okay, that's cool. When I get into the third octet, though, I got a whole bunch that are different. And so life can be really confusing here because you look at this and I can tell by the looks on your face, your first thought is, yeah, there's no way I'm going to be able to put this down into one line. Well, you're correct. Okay, that's not going to happen. But all we said was as few lines as possible. Okay, so the exercise is to think about the binary and what can I group together to make it as efficient as possible for the router or for what my exam is telling me to do. Okay, so it's all about the grouping. I have 2 possible values in the second octet. I have, 3 possible values in the third one. Now we get into another interesting feature called pattern recognition. Good news is the human brain does a lot of things as far as recognizing patterns in things. Bad news is the people who write exams know this. So you will find things displayed to you in a completely haphazard format. If that were written in numerical order, it would be a lot easier to spot the similarities. There are 2 number 3s. There are 2 number 11s. There are 2 number 14s. So from a pattern recognition standpoint, this should automatically jump and tell me if I can't do any further summarization right here, then I can get down and say, there's going to be 3 lines. I can find a way to summarize that second octet to look at my differences in there and not worry about the rest. So a way of doing that is looking at the bit that is different. So when I write my mask out, remember, this bit needs to stay the same, which means that it'll be what in a mask? A 0. So does this one, so does this one. Then I have a 1, and then all the rest are zeros. Working that backwards, that gives me the value of 16. Router thinks that's perfectly fine. Our brain doesn't, because that's not the way that we learn things, but the router thinks it's perfectly fine. And great way to kind of step back out of it. Any patterns? Well, yeah, there's a whole bunch of differences in the first octet, so that's not really helpful. There is in the second octet, or in the third octet also. A 164 and a 165 in some of them. No even distribution. So again, this is one of those you're going to have to play with it sort of thing. Stepping back to the binary, definitely write it out. Another thing that I would suggest you can do on, certainly you can do it on the CCIE lab, which is more where you'd run into this. Use Notepad. Because if your handwriting is anything like mine, after a while your columns are not going to line up, and you're not going to know what the hell your boundary is. So use Notepad. It's a proportional font to make your life a little bit easier that way. But that'll help you see those lines as far as where you're going to draw the what's similar, what's not. So my differences, my things that I'll get to in here. Okay, grouping everything together. My first octet, what do I see that's different? Okay, I have a whole bunch. So can't quite do that. Divide and conquer. That's the best way of looking at it. Right? There's no great pattern answer other than you're still working in binary and you're still looking for those things that are similar and those things that are different. So first step in that, like I said, is the pattern recognition. If I'm starting to move anything in here, can I pair any of those numbers together, when I'm looking in binary, I guess, and reduce the number of differences to them to like 1 bit of difference? So what was that? First and fourth, so 207, okay, so those are both 207, all right. And the second and fifth, so what is it with 208 and 192? Okay, so very good. So 208 and 192, there's only 1 bit of difference between them in the first octet, and the third octet's actually the same. So that'll make it fairly easy to do. First and fourth, both are the same in the first octet, and only 1 bit of difference in the third octet for it. Okay, so great. Great way of narrowing it down. There's actually a couple different ways of narrowing it down in there to make it, but idea being just divide and conquer, split the things out. Right? So keep them all simple in there. So here's your mask for the first one. The 16-bit would be different, and the 1-bit would be different in the third octet for that line. Right? 1 bit at a time. Everything else we just don't care about. Anybody ever watch Roger Rabbit? You guys are all old enough. You've seen that? All right, it's cool. So then at least you'll get the Jessica Rabbit stuff. She had a second career. Yes?
So how did you incorporate the 205?
I typed my mask wrong. Yeah, 205 should have been in here. It should have been a 200255. So note to self on fixing that, which will be fixed, by the way, before it goes up online. So the ones that you guys will be able to download will be corrected. Thank you for pointing that out. So anyway, Jessica Rabbit did come back as a second career in networking. So all sorts of good things. Now, again, breaking things down. Few lines as possible. Think about it. I might take some paper on this one because I put some differences in different places. In fact, we got 3 different octets as far as where the differences are. And you do get to relax a little bit. I will tell you some shortcuts how to do this too. So just write down what the different values happen to be. It's going to start with that one, for each of the octets. So when we start getting there, what we have is 182 and 190. So here they are in binary. Second octet, 17 and 81. Third octet, 73 and 77. Nice thing is we actually have an equal distribution of all of those. There's always going to be 4 of each of them. Again, pattern recognition. This kind of starts to help me out here. So real quick, what's 2 to the third power? 8. Okay, very cool. Here's what my mask is to solve that. Not that this is a normal thing to look at, but again, from a router's perspective, perfectly cool. There's 1 bit in the 8-bit position right here. There's 1 bit in the 64-bit position right here, 1 bit in the 4-bit position right here. Those are my 3 bits of difference that I have. My way to check it, 2 to the third power, means that I will have 8 possible matches. Well, I already erased that. Anyway, so all 8 values being represented. Looking at my list right here, magically, I have 8 things. Right, so I can actually summarize all of those into one single axis list line. Right, so neat stuff. Just when you think it's safe. How would that be on your exam? Good news is we're not going to think about it too much, other than I would say something that whenever I look at this, the first thing I'm going to do is count how many entries there are. All right, because that will help me narrow down how much of a pain in my butt it's going to be to solve it. Another, I suppose, important technique, those who are taking CCIA lab at some point in time, nobody cares what points you get as long as you get 80% of them. So if you see something like this and you don't like it, skip it. On the other hand, if you think it's really easy to do, go for it. It could be easy points. So kind of do your triage that way. But there's 64 things on here. Now remember my powers of 2. Is that an exponent of 2? It is, which may be a good indication that I can do it in one line. Think about it for a little while. So tips and tricks. Okay, let the math be your friend. Okay, let the router help you out also. So kind of like what we were talking about before, as far as if we put the number 2 up there instead of the number 0. Put whatever value you want. The router will always replace it with the lowest match based on the mask that you told it. If the number it comes back with is something completely different, like not on your list, you might have messed up. So always something to think about for it. But also, the number of 1 bits in my mask will, the 2 to that power, will tell me how many matches there will be to that. So right here, I have 7 bits. What's 2 to the 7th power? 128. So if I'm doing the even numbers out of 256 of them, well, kind of divide it by 2, that tells me I'm going to get 128. You're scowling again. You do that a lot. If you do that, I'm going to know you're scowling. Okay. Well, no, so not everything. You can't do everything with one mask. So yes, if I did a 0.0.0.0 with a mask of all 255s, yes, that would permit everything. Now, the good news is I don't think it takes any of you guys, no matter what level you're at, to look at that and say that's going to be a bad idea. Okay? Permit any is not secure. Okay? Mm-hmm. So which one are we talking about? Let me go back to it. But this one? So was that the one you're talking about? Okay. So yes, I mean, I could have had 3 different ones, 3 different lines in there, but the problem is that's not, it's not in as few lines as possible is really what it boils down to. That's the key term. Okay. And what you have to check is are you going to permit more things, either permit not enough things based on the mask you put in or permit extra things that you didn't want to. It would get you less than, well, not from a binary perspective, because you're doing 1 bit. You could do a line that changed, the 8-bit in the first octet. You could do another line that changed the 64-bit in the second octet. No. All right. So when I look at 8 in binary, it's that. I only have 1 I don't care bit in there. If I had the number 7, that would be a 111, and yes, you would be correct with that. Okay, but the number 8 is simply 1 bit when indicated in binary. All right? And don't feel bad about it. That's the big thing. Because this is not how you're trained originally, you don't think in binary. This is what makes it hard at first. All the router thinks about is that the value must stay the same, or I could care less. That's all the router does. It's a very simple judgment call. I would say it's a binary action, but that's kind of a punny answer to it. So that's the way that we think, or the router thinks about it, and that's the way it's good for us to get used to thinking about it as well. Single bit at a time. Now, when we're doing a net mask for like a subnet on a network, yes, we have to draw that line. Bits over here are one thing, bits over here are another. But in an access list, every bit is fair game individually. So the other trick in there is to subtract. Okay, take your two numbers. In the last example, we had, let's see, what did we have? Okay, so 182 and 190 are my two different numbers. Well, what's 190 minus 182? 8. How about that? That's also the answer for the mask. Okay? If the answer that you get when subtracting is an exponent of 2, chances are that's the one bit of difference between them. If the answer is 1, don't trust that because you might be over a bit boundary. Okay? So like I can't get 2 or I can't get 1 and 2 into the same net mask. Not with just one bit anyway. So that would be the exception to that rule. But other than that, anything 2 and up, if that's what your answer is, that's the bit that's different. Okay? 81 minus 17. It's 64. Okay? 77 minus 73. 4. So there's my mask. Okay? I get the answer for each of them. I can quickly look at it. I can say, okay, that's going to be 3 different bits. 2 to the third power was how many? 8. I got 8 things there. I'm good to go. Ready to rock and roll. The match was 8.64.4. Whatever. Whether I'm doing .0 or .255 in the last mask would depend on whether I'm doing routes or a permission for security. Huh? We have a light bulb. No, this is good. But it's one of those things too that working with binary, when you're first sitting down to do it, I suppose let me tell you easily, there is nothing sexy about binary. You will not pick somebody up in a bar, even at a conference like this, by talking about binary. Okay? Just want to lay that out there for you. But yeah, once we get it and you can start to answer questions really quick, that's the part you might pick somebody up in a bar with. But anyway, beyond that. So those are things that we can do to help us out. I already talked about this, about putting in a higher number, letting the router or switch put the lowest value in for you as a way to check things out. Great ways to do it, especially when you get to the really long and convoluted ones. So let the routers or let the equipment assist you in there. In case you do care, by the way, this was the answer to that one. It's a little bit harder because there's multiple bits involved because I have like the 0 through 7 and the 32 through 39 in there. This would be a fun exercise when you get to it. Work it out on paper or in Notepad or something because this is the part that's going to make it click as far as the number of bits and doing those checks and the things like that and what can be permitted. So you're scowling. You're not covering your hands this time, your eyes. Only on the ones where there's 1 bit difference. So like the 0 through 7 and 32 through 39, that's really not helpful for that because it's a range. But otherwise, yes, that would. So that's the IPv4 side of the world. Now, IPv6. Again, from an important standpoint, okay, there's been a lot of changes to the blueprints. CCNA fairly recently, CCNP fairly recently, CCIE definitely now that we moved to version 5 or are moving to version 5. IPv6 is here to stay, like it or not. Not much we can do about it at this point in time. A little bit too late to go back in time. So with that, we need to start thinking about it in terms of all levels of our certification exam. Now, good news is they start out fairly small. It's about addresses to begin with. But even at CCNA level and knowing IPv6 addressing, you still have to have that concept of that net mask and what that's going to be in there. The good news is it's not any different than an IPv4. Now, there are some differences. Obviously, we're going to have 128 bits now. There's going to be 8 groups of 4 hex characters. So here's my other humor for the day. So 1 hex character is 4 bits. That's called a nibble. 2 hex characters is 8 bits, which is called a byte. So 16 or 4 hex characters is 16 bits, 2 bytes. What do you call that? It's a mouthful. Okay? So we have 8 mouthfuls. But whatever we want to call it in there. Yeah, unfortunately, that's not part of the RFC, so nobody's going to buy that one. Anyway, they're separated by a colon, so all the fun stuff. By default, it's 50%, 50%. So halfway through, I've got a /64 essentially. This is my host bit. These are my network bits, or network/subnet bits. And that's the default of the IPv6 addressing specs for how to do that. The whys we can go into if you want to, but there's whole other IPv6 courses on that. So when I start looking at things in here, I will also break down my numbers. I will dispose of leading zeros. I will also collapse contiguous zeros into a double colon. IPv6 addressing, very important to know. All of your levels of exams, you will have some question that says which of these are valid IPv6 addresses, because they like to mess with your head. Welcome to Cisco networking. So those are the basics to it. Now, a comparison. IPv4 addresses. They're nice, they're cute, they're cuddly, mostly because we're used to them. They may still have fangs. IPv6 addresses. If you have to deploy IPv6. So anyway, all the fun things. IPv6 by itself, from an addressing perspective, was designed to give us hierarchical summarization. Okay, the way things were set up is that they were going to allocate at ISP levels, like a /32, and that every enterprise would get a /48. Now, what's 48 minus 32? 16. All right, so that means that every enterprise would automatically, or every ISP would automatically have 16 bits worth, okay, or 2 to the 16th power is like 64,000 or 65,535, would be able to have that many subnets to allocate to their customers. An enterprise has a /48. Every network in IPv6 is supposed to be a /64. What's 64 minus 48? Same answer. It's also 16. So again, every enterprise with a /48 application should be able to have 65,535 subnets, or 536 subnets. All right, so a whole lot. Basically, the idea in IPv6 is we have many more addresses than we need. Okay? In case you care, 2 to the 128th power is 340 undecillion, otherwise known as a boatload. So lots of things that we have. But when we get into talking about things like allocation strategies, or more importantly, subnetting strategies, it's still all about the line. Hey, where we're going to draw that line and what we're going to do with which of the bits. So if I have a network, so I'm allocated a /35 network, that means the first 35 of my bits are my N bits, okay, my network bits. That's my starting point. Just like in IPv4, if I were told that you had a class B address, you know that you have 16 bits that are network, N. They're not going to change at all. And then you want to allocate some /48s out of the /35. Okay, seems reasonable. What's 48 minus 35? 13. There you go. So I can draw it out, and I know that the next 13 bits right here are going to be the range that I get to play with, or that I get to increment in, right, and see how many of those that I happen to need. Well, 2 to the 13th power tells me there's going to be 8,192 of them. So that way I can tell how many subnets I may be able to get out of that, just by the difference for what I'm going to be told to allocate versus how many I have to begin with. And the bits are all working the same in IPv6. It's butt ugly when we get to hex. Now, the cool thing is you can spell stuff. It's all the fun things. There's been a couple guys that are around here that I really like. Facebook. FACEBOOC, but that is actually the IPv6 allocation they have. How cool is that? Start to rename your companies to only have F and lower as far as your values. Would be kind of fun. But anyway, the thought process, however, so everything we've learned about IPv4 subnetting, as far as my blocks and everything else like that, is exactly the same in IPv6. Process be a little bit different just because they are uglier addresses, and we have to think of things from a hex standpoint now as opposed to decimal to binary. Okay, so hex to binary conversion be a little bit different, but the concept is all going to be the same in here. So, if I wanted to change things as far as giving out /40s out of that /35, well, I'm still good because all I'm going to do is just move my line further. however many of these that I have. So 5 bits now from the /35 to /40 means I can have 32 of them, or 8 bits from the 40 to 48 means I got 256 of those. I can allocate my lines wherever I need to determine how many subnets I'm going to have, or what we call next level aggregates in the IPv6 world. So remember I told you about that hierarchy thing, all those triangles that we're adding up? That was a thought process when they came out with IPv6. Is that one level of an ISP would get, a /32. The next level down, so like AT&T or something. The next level down, mom and pop's ISP may get a /40 out of it. Still, every enterprise is supposed to get a /48. So we just shift that line for what my starting point is. It used to be 32, now it's going to be 40. Then I want to get to 48, but that gap in the line there for where we're going, those binary values, is going to tell me how many things I'm being able to look at or where my allocations are going to be. The good news, by the way, for IPv6, they will not ask you how many hosts will be on a subnet. There's a lot. So you're good for that standpoint. But from a subnetting point of view, we will still have to do that portion. So how do the allocations work? Again, pick your numbers. Once I get into this and drawing my line, all the rest of the math stays the same. So here's my hex ones, by the way. I just broke out these two groups into binary so that I could draw my line in there. So I've got, 16 plus 16, so 32, 33, 34, 35. So this was a /35 that I was originally allocated. 36, 37, 38, 39, 40, 41, 42. So here's my 42s, and then this will get me up to 48. So I originally had the 35, and I get this in here, so there's 7 of those? 1, 2, 3, 4, 5, 6, 7. Okay, so 2 to the 7th power. Whatever things that I happen to be doing, that's my bit of difference. When I start looking at that from what my values are going to be, and we'll get into this in a moment, my binary game, so let's just pick on the 3 bits just to keep it simple. If all I have is 3 bits to play with, I know what values I can represent. The all zeros, the 001, 010, you keep counting in binary. Those rules don't change whether I'm doing IPv4 or IPv6. Part of the problem is, from an IPv4 perspective, we usually don't think in binary, unless you're doing the strange access lists and cool stuff like that. Just because that's not the way we're programmed to, so that's not the way we typically do that. In IPv6, there's really not a whole lot of getting around it, because just like we don't think in hexadecimal, we don't think in binary. So we're going to have to pick something one way or the other. If you can do it in hex in your head, awesome, more power to you. I can't do that. I just don't choose to wire that way because everything breaks down to binary, so to me that's easier. But whichever method you want to get there with, all the rules are going to be the same. So here's something that might show up on an exam from an IPv6 addressing standpoint when we get into mixed allocations, because this is the part that's going to test. That just forward itself? Same one? Okay. But this is the part that's going to test how you do your numbering skills, where things are going to be and what values you're going to come up with. So I may have to have, some guys with a /40, some guys with a /41, some with a /42. I'll tell you how many of each in there, but you've got to give the network numbers. So it's not just picking how many I can have, but you have to tell me what those networks are going to be. That's what makes it fun questions. There is a draft spec, just in case you cared, but still relevant things. I don't want to do that. So hang on. So if I'm going to break things down, and I want to end up with something that gives me this. I want 2 /34s out of there, 3 /37s, and 5 /38s. It's all about bits. Just like in IPv4, start allocating from your larger ones first, because those are going to give you your bigger block sizes. So always carve them out that way first, and then allocate to the smaller ones. Rules haven't changed. We do the same thing in the design context of IPv4. Are any of you doing CCDA or DP? Okay. So you may run into those questions as far as the different block sizes on there too. So out of the things that we have, take the bits. So my first bits right here are going to be where I'm going to start carving things out of as far as my /34s. So remember, here's my first 32 bits. There's bit 33 and there's bit 34. So that's where my first line has to be drawn. So I get a 0 network and I get a 1 network. Those are now all used up, so that's kind of cool. So now what that means is that my next things, whatever I'm going to carve out, all have to start with 1 0 in those 2 bits, because these are already taken care of. But going from a /34 to a /37, that means the next 3 bits are what I'm going to be concerned with right here. So again, moving those in binary. Got my all zeros, got 0, 0, 1, got 0, 1, 0, so equivalent of 2. If I had to stick an extra 1 in there, that would be what? 0, 1, 1. So I can kind of get into all of this notion as I go. If I'm not going to account for anything else along the way, so we don't need to worry about setting some aside for future growth, then I would immediately go into my 0, 1, 1 and start going to the next bits, or next bit, which doesn't show up very well here. So between a 37 and a 38, that's 1 bit of difference that's going to be in there. So my 0, 1, 1 right here, I have a 0 bit. 0, 1, 1 right there, I have the 1 bit. Now I'm going to have to move my next 3 bits to the next value. So 1, 0, 0, have a 0 bit. 1, 0, 0, have a 1 bit. 1, 0, 1, have a 0 bit, so on and so forth. It's all about incrementing the binary game, but based on each of the lines that I happen to draw. Right? Once we're done with that, then we get to convert it back into hexadecimal. Why? Because that's the way the router makes us do it, or at least the iOS programmers make us do it. So you will have to work on hexadecimal to binary conversion. Good news is it's actually simpler than decimal conversion because you only got 4 bits for each character. So technically it should be easier. You only got 16 variants. But there will be a lot of that as we move into the IPv6 stuff. I would strongly suggest getting a handle on it as soon as you can, because it will be becoming more and more integrated into each of the exams. Interestingly enough, how many of you are not from North America in here? Okay, a couple of you anyway. IPv6 deployment in other countries is significantly further along than what it is here. Now, you can see all sorts of reasons for it. Most of it is because we have most of the IPv4 addresses. Haha. So it's one of those things. So, there's not as much reason for us to change. But as everybody else changes and moves forward, you're going to have a lot more disconnects as far as who can talk to whom or problems in doing so. So we are going to be moving towards IPv6. Even ARIN, which is the registry for the North America group, is down to less than a single /8 for allocation. I think they're at like 70% of that right now. So a whole lot less addresses than what we'd want to as far as assignments. And a whole lot more companies keep coming up online, or ISPs growing, saying they need more addresses, need more addresses. Bottom line, it's not going to happen. Going to have to upgrade soon. So as we start to all do that, and as we start to get to that, need to be able to think about these things, be able to do our allocations or our subnets and figure that out. They will also be coming onto the exams that way. So that's kind of the fun stuff that goes along with it. And I just converted it back to hex in there. But anyway, in IPv6, just kind of a couple side notes for things. More often you are going to see prefix lists rather than access lists. So, other than from a security standpoint, but in routing, we're going to do things with the VLSM notation. So you can be a lot of slash characters and thinking that way. Again, gets us back into this binary game of knowing where to draw that line and knowing how many bits there are on the other side. So cool thing is you won't have to write out a big, long, ugly net mask or anything like that. Can you imagine doing something like this? That would suck after a while. Right? So instead, this is what we'll end up with typing. Much, much easier. But we have to get used to thinking that way as far as knowing where that line is drawn and what we're doing with it. Okay? Rules don't change, just the way that they actually happen to be portrayed in there. I do have a couple exercises as far as stuff we can go through if you'd like to. We do have still time in here, but this is the method of doing exactly the same type of thing, as far as a summary address anyway, in IPv6. Right? So you could be given a number of different networks, a number of different things in here. And what do we have to do for a summary? What was that rule we came up with? What are we drawing? The line. There we go. Okay? We're figuring out where that line is going to get drawn, which is the first point of wherever there's a difference as far as binary is concerned. So as I start looking at that, I can kind of take it this way and look at it here. Okay, that's kind of my C and D. That's perfectly cool. But from binary, my difference is actually right here. All right, because a C and a D are still going to be the same for the first three characters. So 16, 16, so that's 32, 33, 34, 35. That's where my line is drawn in order to get a single summary route that will summarize all of those networks. It would have to be a /35 in there. Okay. So one more, just for fun. And we just moved which mouthful we happen to be talking about now. But idea still being the same. Break my stuff into binary, figure out where my line is going to be. I did put the leading zeros back in to make things a little bit simpler to see. But we get into here, and there's where things separate. There's going to be my line of difference. So counting it out, I've got 16, 32, 48. Now these are hex characters, so they're 4 bits apiece. So 48 plus 8 is 56, okay? Then 57, 58, 59. And that's the summary that I would have to come up with in IPv6 in order to summarize all of those addresses. So I'm doing the exact same exercise of drawing that line. I'm just putting it all in binary and doing that, okay? Making my difference. Cool? Good, bad, ugly? Okay, some of you are starting to look like the cats. Some of you don't have enough hair to look like the cats. But that's okay. Yeah, there you go. All right. Yeah, this is where we go into the, oh my God, what have I done? Or whatever 4-letter thing you want to put in there. But bottom line is questions, thoughts, comments, root remarks. Are there good ones out there? Not really that I know of. Play around. It is. So, well, I mean, think about it. Whenever you practice doing anything, it's slow at first. Okay? You'll get used to it more and more. You'll get stuff that will start to make sense more and more in there. Okay? So there's always the things that go along with that. I do want to hit you up on a couple things before you bail out of here too much. We have things as far as you guys can win money, which is always good, especially if you want to spend money while you're out traveling. We have a My Favorite Speaker contest. You can feel free to nominate whoever you'd like. I would obviously prefer that it was me, but I'm not picky that way. Do have a few hashtags, so if you are tweeting, put the person's name in there. Now you can substitute this Twitter handle for any other person's name. I'm okay with that. Put that in there, and you must put the different hashtags as far as enabling it for COUS and for the My Favorite Speaker thing in order to get registered to be able to win your money and have the fun stuff that goes along with that.